Welcome to the 36th lecture of graph theory. In the last class, we considered the question of deciding an upper bound for the Ramsey number and getting a lower bound for it. In the last class, we showed that R of k is less than equal to 2 to the power 2k minus 3. Right, this by using a usual combinatorial argument. Now, in this class we are trying to get a lower bound for R of k. R of k is greater than or equal to 2 raised to k by 2. This is our intention today. Recall that the Ramsey number of k is the minimum integer n, we can say n of k. So, okay, R of k such that if the number of vertices in the graph is greater than or equal to this number, then we are guaranteed that either a complete graph on k vertices or an independent set on k vertices is available in the graph. Now, the question is to decide R of k. Finding it exactly is difficult. So, we showed that, but this number has to be less than 2 to the power 2 k minus 3 yesterday. By more sophisticated arguments we can probably improve a little bit, but we are not interested. So, we in that now. So, as of now we just are happy by saying that there is an upper bound for this, there is indeed a number like that R of k. Then how do I show a lower bound for this thing? So, when I say 2 raised to k by 2 is a lower bound for R of k, it means that I can show a graph on 2 raised to k by 2 vertices such that neither it has a k clique in it nor it has an independent set on k vertices in it. Such a graph exists. How do I show this? So, it turns out that the best way to attack this problem is by using the probabilistic method. So, this is what we are going to do now. So, we will show that for every integer k greater than or equal to 3, the Ramsey number of k satisfies R of k is strictly greater than k by 2. So, here strictly greater. Now, we will prove this thing now. To prove this thing, we will consider the probability distribution of graphs g n half. Here we are taking p equal to half, and then so this is, we can write it like a little Carl G. So, so we are taking a graph from this distribution randomly, a random graph we are considering with respect to this probability from this probability space. And then let us ask this question: what is the probability of having an independent set of cardinality k in this graph? And then we ask the question, what is the probability that G has a complete graph on k vertices in it? See, if both these probabilities are less than half, then the probability for one of these two events to happen will be less than half plus half, namely 1. So, that means the probability for the complement event to happen, namely the probability that the graph has no clique of k vertices and no clique of no independent set of k vertices will happen with some positive probability, non-zero probability. which means that there indeed exists one outcome, one graph in this probability with respect to this probability space with this property, namely no clique on k vertices, no independent set on k vertices. So, to prove this thing, we will formally consider what is the probability that G has k in it, right. What is the probability? How do we have already found a way to upper bound this thing. This is less than equal to n choose k, because there are n vertices, and from this n vertices we can select k vertices in n choose k vertices. Now, this probability that this k vertices indeed form a k clique is 1 by 2 raised to k choose to, that k into k minus 1 by 2, is not it. So, this is essentially how much is this? This is n into n minus 1 into n minus 2 into up to n minus k plus 1 divided by k factorial into 1 by 2 raised to k square by 2 minus k by 2. So, this numerator here n into n minus 1 into n minus 2 into n minus k plus 1 can be substituted with n to the power k, because there are k terms here, and each of this term n minus 1, n minus 2, n minus k plus 1 all are less than equal to n. So, I can simply write this is less than equal to n power k by k factorial into 1 by 2 to the power k square by 2 minus k by 2, right. That is what I can see. Now, k square is greater than, or we know that k factorial is greater than equal to 2 raised to k. Why is it true? Because for instance, k equal to 1, this 1 factorial is need not be greater than equal to, it is not greater than equal to 2 raised to 1. So, but k equal to 2, 4, k, this is 2 factorial, that is 2, how can it be greater than equal to, sorry, I am saying, so you can so when you put 3 here, we get when you go put 3, we get 2 raised to 3 is 8, then this is 3 factorial is 6, right. So, therefore, we can substitute by so we can say 4 factor. Okay, so when k factor, for instance, this is in fact 1 into 2 into 3 into 4 into 5. So, say for instance 5, so then we can say this is 2 raised to 5, this is 32. How much is this? So, this is 6 into 4 into 5. So, we have 120 here. So, 20 into 6 is 120. So, this is bigger, right. So, now with 4 we have 1, 2, 3. So, this is 24, and here it will be 2 raised to 24, 2 raised to 4 is 16. So, 24 is greater than equal to 16. This is also true. With k equal to 4 onwards, this is true. K equal to 4 onwards, this is true. while k equal to 3, what will happen? This is 6 only, while this is 6 only, while this is 8. So, that is not true. So, we have to assume that k for this to be true, for assuming that k factorial is greater than equal to 2 raised to k, we should assume that k is greater than 3, right. Let us assume that. So, what will I do for k less than equal to 3? So, that we can easily verify, because you know r of 3 is equal to 6, r of 2 is equal to 2, and so on. So, when you put 2 raised to k by 2, you know, all these things, it will be immediately clear. For instance, put k equal to 3, 2 raised to 1.5 is less than 6. So, put k equal to 2, 2 raised to 1 is less than equal to 2. So, for k r greater than equal to k greater than equal to 3, we will prove that, otherwise so we have to put r of k greater than equal to 2. Now, so our statement of the theorem only is being proved for k greater than equal to 3. For k equal to 3, we can easily check it, but because we know r of k is equal to 6. For k greater than equal to 4, we will do this thing by observing that. So, in this k factorial can be substituted by 2 raised to k, because k factorial is greater than equal to 2 raised to k for k greater than equal to 4. So, now we will get this thing. So, like this is less than equal to n raised to k by 2 raised to k into 1 by 2 raised to k square by 2 minus k by 2. When I now suppose n is a number which is less than equal to so suppose I take n equal to 2 raised to k by 2. So, let us take this number. Now, I can substitute this by, so this is less than equal to 2 raised to k square by 2, because I am putting n equal to 2 raised to k by 2. So, this is by 2 raised to k into 1 by 2 raised to k square by 2 minus k by 2. So, this will be, so here cancelling this and this minus, so we will get less than equal to 1 by 2 raised to k by 2. Now, I have assumed that k is at least 4, because k equal to 3 case is already considered. So, this will be less than equal to, so if I put the smallest possible value here, k equal to 4 is 1 by 2, right. So, I get that it is less than equal to 1 by 2. So, what we have now done is the calculation of the probability of this event. G has a kk in it, an induced complete graph on k vertices in it, right. So, we just did it by considering all possible k subsets, and we calculated the probability that it should be suppose given a k subsets, what is the probability that there is a clique on it? That was this probability, because there are k into k minus 1 by 2 edges. 1 by 2 is the probability that an edge occurs, and then we multiply by n choose k, because we were summing up over all possible k subsets. If any one of them has a clique, then we have a k clique. So, then we can upper bound it by that. So, this can be, this actual probability can be much smaller than this total sum, but then we can upper bound it this way, and then we substituted this thing. This is replaced by n raised to k, this is replaced by 2 raised to k. For that, as we calculated and so, we needed the assumption that k is greater than or equal to 4, because k equal to 3 unless it is not happening. So, therefore, when the, but then below it is clear that 2 raised to for r of k we know the values, therefore, we do not have to bother about it. So, and now substitute it, and then we cancelled all the things, and then we finally, so we also substitute n equal to 2 raised to k by 2. For instance, if you take a graph with 2 raised to k by 2 vertices, then we can substitute n equal to 2 raised to k by 2. So, then we show that this cancels out, and is because we have assumed that k is at least 4, we can see that this is less than equal to 1 by 2. So, this probability that G has a k in it is less than equal to half, sorry, strictly less than half. So, here, so it is not less than equal to, this is strictly less than half, because we have substituted with bigger values here, right, less than, strictly less than. So, here somewhere here, so for instance, when we substituted by n raised to k itself, we can put strictly less than, right. So, strictly less than half. Now, similarly, the same, we can calculate the probability that G has a Sk in it. What is the probability that Sk is the independent set of size cardinality k? That will also be strictly less than half. So, the probability that G has either a kk or an Sk in it is actually less than equal to sum of these two probabilities, this and this probability that it has a kk in it, and the G has an Sk in it. So, when you sum up it, this is 1. So, this is strictly less than half, sorry. So, because this was strictly less than half, this is less than half. So, the total will be 1. So, this is the probability that either kk or Sk in it will be strictly less than 1. So, there is a non-zero probability, namely 1 minus this value, right, that G has neither a kk nor an Sk in it. So, this is because we have taken n equal to 2 raised to k by 2, right, the upper bound is this much. So, now we can infer that the desired event, namely there is no kk and no Sk in the graph, has a probability of probability which is non-zero. That means there should be a graph with the desired property, otherwise we will not get a non-zero probability for that event. Recall that the event's probability, event corresponds to a set of outcomes, the set of graphs in our case, right. When I say that this property has a non-zero probability or this event has a non-zero probability, there should be some graphs belonging to that, otherwise we will not be able to get a non-zero value for that. It means that there exists a graph with the desired probability. So, the inference is finally that if you fix your n equal to 2 raised to k by 2 or maybe less than that, less than equal to 2 raised to k by 2, we can always find a graph with the property that there is no kk in it, no Sk in it. So, the Ramsey number R of k has to be strictly greater than 2 raised to k by 2 as long as k is greater than or equal to 3. This is what we have inferred. So, this is the basic way we apply the probabilistic method. So, here we wanted a particular graph with two desired properties, that is there is no kk and there is no Sk. So, what we did is we looked at the complement events, namely there is a kk, there is no Sk. So, one of them happening, the probability that one of them at least happening is less than, strictly less than 1. So, by we could add up because we are looking either this or that. So, and then because it is strictly less than 1, there should be a probability for the desired event. Now, our intention is to introduce some other techniques of probabilistic method. So, we will start with the notion of expectations. So, let us see. So, what is the mean or expected value of a random variable x? So, let us not get too much into the details of probability theory, but let me remind that random variable is a real valued function, but in our case when we are considering the GNP model, especially when we are dealing with graphs, usually our random variables will be some of the graph parameters. It can be the chromatic number, it can be the independent cardinality of the maximum independent set, or any such usual graph parameter, which means that typically they will be non-negative value 0, 1, 2, 3 like that, right. It can be the cardinality of the maximum clique, so or even number of edges. So usually we will have these x taking values 0, 1, 2, 3 etc. And the expectation of the random variable x is defined to be sigma of g element of g and p, here for in our case g and p, p of g into x of g. So for a given graph in g and p, let x of g be the value for one outcome, say for one graph x of g be the value of that random variable, multiply it with the probability of that particular outcome, particular graph, and then sum over all such outcomes, possible outcomes in G and P. That will be the expectation of x. So this is the usual definition of expectation. We just wrote it in terms of the G and P probability space, that is all. And now, so we will just look at some examples of finding, how do we find expectations. So there are one way of finding the expectation is to look at each possible graph and find out the probability of that graph, and then find out the value of the random variable in it and multiply the probability with the random variable and sum it over all these things. But many times this can be very tough. So usually we go in a different way. So to illustrate this point, we will take up the following question. So let us consider this question of counting the number of k cycles in a graph. What is a k cycle? A k cycle means say cycle with exactly k vertices in it, like this, right. So it is a simple k cycle. So 1, 2, 3, 4, 5, 6, this is a 6 cycle. In a given graph G, how many k cycles are there, right. So now I am interested in this parameter x. So that is the number of k cycles in the random graph G. So this is a random variable. Now how do I find the expectation of x? One possible way is as according to our definition of expectation, the way we have defined expectation. So we can, so the way we have we can consider this probability for each g and then find the value of the random variable, namely how many k cycles are there in it, and multiply them together and sum over all possible graphs. But then this is very tedious, it is not possible to do that in many cases. So here we will find out a different way. What we are going to do is to define a lots of so called indicator random variables, namely, so given a graph G, so we can find out each possible cycle. Each possible cycle means, see for instance, this can be a possible cycle. So 1, 2, 3, 4, 5, 6, this is a possible 6 cycle. If all these edges are present in the random graph, in the graph that we have selected, then this k cycle is present in it. So for instance, you can call it C1, then associated with C1, then I can define a random variable called xC1, and then I can define that xC1 equal to 1 if all the possible edges have appeared here. Otherwise I can say that the random value of the random variable is equal to 0, it is 0 or 1 variable, right. It is an indicator variable which indicates whether this vertices, this collection of vertices in this order provides a cycle or not, right. And then it is very clear that if you can sum up the indicator random variables for all the possible such cycles, and whether, because if the cycle has occurred it will count 1, otherwise it will count 0. When you sum up, we will get exactly the number of cycles that have occurred. So, there are two issues here, how many such possibilities we have to consider. So, one possibility, so for instance we consider n vertices, then there are k cycles we are interested in. So, from n vertices we can get n pk k tuples, or maybe the sequences of length k. So, for instance I can take k objects from n things and then I can order them in a certain way, n pk ways we can order them, that is n into n minus 1 into n minus 2 into like n minus k plus 1 ways we can order them. If you order them, but then will it always correspond? So, all of them corresponds to distinct cycles. For instance, if I get this is 1, this is 10, this is 11, say this is 9 and this is 8. So, for instance k is equal to 5. So, this is a cycle, but then you can see that. So, if I had considered, so for instance I can say that 1, 10, 11, 9, 8 can give rise to a 5 cycle, but then if I had considered 10, 11, 9, 8, 1, that also gives rise to the same cycle for the same order, but then we started from a different place, that is all. So, we could have, for as in the case of a k cycle case, we could have started from any of the k of the any of the k numbers and we could have ordered them, that they all of them correspond to the same cycle, right. For instance, this sequence and this sequence correspond to the same cycle, because the same cycle will come, but just that we started enumerating from here, or say first we started enumerating 1, 10, 11, 9, 8, the next time we are enumerating 10, 11, 9, 8, 1, that is all. Another possible way the same cycle can occur is when we enumerate say 10, 1, 8, 9 like this in the opposite order, also, or maybe this could have been enumerated as 1, 8, 9, 11, 10, right. So, for starting with each vertex I could have listed the members either in the clockwise order or in the anti-clockwise order. There are 2k possible ways. So, this is an overcounting for the number of possibilities, you have to divide it by 2k, because each actual cycle may correspond to 2k different such sequencing, right. So, therefore, npk by 2k possibilities are there, n into n minus 1 into n minus k plus 1 divided by 2k, which we can also write it as n k, this npk, it is another notation for npk, divided by 2k possibilities are there. Now, for each of them I can define a indicator and random variable, say x1 for the first among this, x2 for the second among this. So, x, so n choose k by 2k for the last one, right, and this each of them will become 0 or 1 depending on whether that cycle appears or not, depending on whether that cycle appears in our random graph or not. And now the question is, what is the probability that xi is equal to 1? What is the probability that xi equal to 0? For xi equal to 1, the probability is calculated like this, because for this sequence of vertices we need this edge to be present, this edge to be present, this edge to be present, this edge and this edge to be present. All the edges have to be present. That will happen with p to the power k probability, and this will definitely happen with 1 minus p to the power k possibility, right, because this edge occurs with probability p, this edge occurs with probability p, and this also, this also, this also, this also, and they should all occur simultaneously, and because they are all independent events, the probability that they all occur simultaneously is p to the power k. So, now what we see is the expectation of xi is equal to p to the power k into 1, because random variable takes 2 values, and 1 minus p to the power k into 0, and this term does not contribute anything. So, the expectation is just p to the power k. Now, what is the expectation of x? So, expectation of x is essentially expectation of x1 plus x2 plus, so x and choose k by 2 and pk by 2k, right. So, all the random variables are to be added. As we have observed already, this random variable essentially is the random variable which counts the number of cycles, and each of these random variables indicates whether a given possible cycle has occurred or not, and this many possible cycles are there. When I sum them up, all these things which have become 1 will contribute. That means that actually how many cycles have occurred, they will be counted, and that is exactly this x. Therefore, x is equal to x1 plus x2 plus this thing. This is the trick, and then the expectation of x can be counted by finding this thing. The one good property about expectation is that it is linear. That means this expectation is essentially the sum of the individual expectations. The expectation of the sum of random variables will be like we can calculate like this, where we can simply sum the expectation of these things, right. So, this is expectation of x 2k. So, this is the way, right. So, if we sum up all of them, so which means that each of them is p raised to k. So, I can simply multiply by p to the power k, or n p k by 2k into p to the power k will be the expected value of that. This is an easy way of calculating the expectation of x. So, what we have now showed is a method to calculate the expectation of this random variable x, which is which counts the number of cycles in the random graph, k cycles in the random graph. So, again to repeat, the trick is rather than using the direct definition, namely for each outcome, find the value of the random variable and multiply with the probability of the random that particular outcome and sum over all outcomes. We rather do a different kind of counting. That means within each item, what are the possible possibilities, what are the possible objects which can be counted towards our random variable. For each of them we will define a indicator random variable, then we will find the expectation of that and then we sum over. That is this idea of the indicator random variable is a very commonly used technique. The only new notion we have introduced here is the linearity of expectation, namely when you have two random variables, say x and y, and then if you can multiply with the scalar ax and then b into y, this is essentially e into expectation of x plus b into expectation of y. This proving this is trivial in fact. So, if you try it you can prove it yourself, but then this is a very useful property in most of these calculations. We will not be, for instance, if you do use the usual definition for this thing, it may be very difficult, but on the other hand once you expand like this, calculating this and this can be much easier, and then we will be able to calculate this using this. So, this property, namely the linearity of expectation, is a very useful property. And um, now that we have introduced the expectations, we will introduce one inequality related with expectation which becomes very helpful. This is called the Markov inequality. So, the Markov inequality says let x be a x greater than equal to 0 be a random variable, and okay, it need not be in G and P, but let us say it is a positive random variable, and then consider a value greater than 0, right. Then the probability that x greater than equal to 0, it is a greater than equal to a is always less than equal to expectation of x by a. This is the important thing. So, we are considering random variables which takes positive values here, and then we are claiming that the probability, this probability, namely probability that the random variable takes value greater than a is less than equal to the expectation of x by a, expectation of x by a. So, the proof of this can be easily seen from the definition of the expectation, because this expectation of x is essentially you can see that this expectation is when you sum over all possible outcomes and the with and multiply by the value of the random variable, and then and the probability. So, we can in fact see this as sigma over the value of the random variable, right. So, the probability that, so of course, for instance, when you discard the values which below a, some of them are discarded, we can easily see that this is essentially probability of x greater than a. So, all the we are considering only the values of x which are greater than or equal to this, and now each of the values the corresponds to something greater than a, right. So, therefore, so this will be greater than or equal to. So, what we are going to do is the expectation of x. So, for each possible value of x, we have to multiply it with the corresponding probability. What is the probability that x takes this value into this probability, and then we sum them together. So, suppose we drop all the values of this random variable which are less than equal to a, then and consider only those probabilities which are greater than this. So, this is definitely, this expectation is definitely greater than equal to probability that x greater than a and into a, because all the values are at least a here, x is a or more, right. For all of them together the probability is this much, then I am substituting by a here. Therefore, this probability alone will be probability of x greater than a will be less than equal to expectation of x by a. This is what. So, this is just from the definition of the expectation and the fact that a is greater than equal to 0. You can get this from there. So, this Markov inequality which is which gives us an upper bound for the probability that x greater than equal to a in terms of its expectation is quite useful in many situations. We will be using it. Now, for illustrate all these things, the expectations, the use of expectation, the use of Markov inequality, what we are going to do is we will take one interesting question which was one of the earliest questions in the in this area, which was proved by Erdős. So, what is this question? So, it consider this question. So, do we have consider this question. Suppose we are given an integer k, and we are looking for a graph with girth greater than k. Girth means what? Girth means the shortest cycle length, the length of the shortest cycle should be greater than k. And also another property is required for the graph, namely the chromatic number of the graph is also greater than k, two numbers. You can always, so for instance, the question can be asked differently. You can say that I want the girth greater than k and the chromatic number greater than k, but that is fine. We can always change by taking the bigger of the two and then ask this question where both values are same. So, I want a graph that the girth is greater than or equal to something and the chromatic number is. Is it possible to find a graph always like that? I am allowing you to make it big, that is not a problem. It is, you can always decide that the number of vertices in the graph is big, but then is it always possible? Why do we think that it may not be possible? That is because these are kind of contradictory properties. When I say the girth is greater than k, if you look from one vertex, you will see a tree like structure around it because there is no short cycles. So, you have to go some distance and it will look like this, for instance. So, if I look from this thing, so you will see a structure like this to some distance until k by 2 there will not be any. If you go, for instance, if you see a structure like this, that means there is a short cycle here, right. So, to some distance you will not see any edge blocking the tree. So, it means you may look like if you give a color to this thing, you can give a color to these vertices and then you can give the same color here. So, it is like a bipartite graph, it is two colorable graph, locally two colorable graphs. So, does it mean that somehow if not 2, so can I use 3 color or 4 color or some constant number of colors, a small number of colors, so that it can be colored, because from looking from one vertex it look like there is not much conflict in the vicinity of that vertex. From each vertex it is the case. It gives us a feeling that probably the chromatic number of this thing is high. That is why we asked the other question, can I keep the chromatic number of the graph also high? I want both this conflicting parameter to be high. When the chromatic number is high, we may get the feeling that the graph is dense, and then because it is dense there may be short cycle in it, right. So, that is why the other condition is conflicting. That means we want the chromatic number high and also the girth high, there should not be any short cycle in it. So, intuitively these are two conditions which are kind of conflicting with each other. So, this question was not easily answered, while it is very easy to or it is not very difficult to cook up graphs for small values of these parameters, but then when in the arbitrary case, when if you allow any k, so how do you prove that such graphs exist? So, Erdős very cleverly used the probabilistic method to prove that such graphs exist. This is the next interesting theorem that we want to do. So, to prove this thing, we first will see how we can use the probabilistic method. See, what is the difference here from the previous problem? The previous problem also asked for two properties together. That means we do not want a complete graph on k vertices in the graph, and also we do not want an independent set on k vertices in the graph. This we wanted to coexist, both these properties we wanted together. So, for that what we did is we considered the complement property, there is a k in the graph, complete graph on k vertices. There is the other event was there is an independent set of k vertices in the graph, and then either this or the other, one of these events can happen with probability equal to sum of the individual probabilities at most, right. Then if this sum was less than 1, then we know that the complement eventually neither kk nor sk occurs can happen with certain finite probability, right. So, this same technique, why doesn't why can't we apply in this case also? Here also there are two properties. I want the girth to be high, I want the chromatic number to be high. Let us consider the probability that the girth will be the probability that the random graph that I have drawn, the girth of it will be small, right, there will be a certain probability for that. And then consider the probability that the the chromatic number of it, if at all, if I can directly deal with it, independent chromatic number of this thing is also small, less than k, right, and then sum the probabilities and show that it is less than 1. But it so happens that if I fix p equal to half, this will not be possible. So, but then why do you want to fix p equal to half? Try to fix p, the suitable p, that is the thing. How can I fix a suitable value of p so that both these events will happen together with some non-zero probability. So, to do this thing we to do this thing, what we are going to do is to first consider corresponding some we have to adjust this probability value p. So, but it so happens that if p is reduced very much, then the chromatic number will increase. How do you find the chromatic number is? So, the only handle we have to deal with chromatic number is to show that the biggest independent set in it will be small, because if the biggest independent set in it is small, the chromatic number has to be high, because any color class has to be an independent set. If each color class is small, then we need many colors, right, then we need many colors. So, we will try to keep the independent set size small. But if the probability p is small, for instance, if I take p is equal to some c by n, where c is a constant, we can see that there will be large independent sets. But on the other hand, if I keep the probability high, so that I can keep the largest independent set small, then we can see that there is surely we are going to get short cycles. So, if we try if you work out the calculations for various p's, we will see that such a p will not exist. We cannot make it happen together, both avoiding the short cycles and independent sets. So, then what will you do? So, to get a feel of this thing, it so happens that if so when, for instance, if I want the alpha to be greater than or equal to n by, so the probability that if I want the probability that the biggest independent set size is greater than or equal to n by k should tend to 0, suppose. If that is what I want, what should be the probability value I should give? So, it turns out that if I give the probability p greater than or equal to 6k log n by n, then we can make this happen. But then unfortunately, this is already too high for the other event. So, why am I trying to make alpha greater than or equal to n by 2k? If anybody is confused about it, this is because if I prove this will immediately imply that chi greater than or equal to n by alpha equal to n by 2k, right, n by 2k is greater than or equal to 2k. In fact, I do not need 2k, I can put n by k. So, even n by 2k. So, here this is what we are going to first prove, but so to prove this thing, so how do we do that? We have already done certain calculations for that before. So, because the probability that there exists an independent set of greater than n by 2k, right, that will be let us say greater than or equal to some t value. So, that will be we know that this probability is less than or equal to, so we can actually calculate it, because so suppose you take the a set of size t, let us see if I take a set of size t, and what is the probability that there is an independent set. So, because we can always say that the all of them, right, there are t into t minus 1 by 2 edges. So, all of them should be missing. So, then the probability is q into t minus 1 by t, but then the probability that such an independent set will occur is at most n choose t times q into this thing. So, n choose t times q raised to t into t minus 1 by 2. This is the probability, right. Then we see that this is at most n raised to t. So, we can just discard the n choose t part, and this is q into t into t minus 1 by 2. What is q? Q being 1 minus, q is equal to 1 minus p here, right, because p is the probability of an edge to occur, q is equal to 1 minus p is the probability that that edge will not occur, right. This you can write it as n q into sorry n into q raised to t minus 1 by 2 whole power t, right. Now, we want to know when will this tend to 0, when will this become 0 for large enough n, as n tends to infinity. If I want this probability to tend 0, what should be the value of q? In fact, I am interested in the value of p, that is what. So, it so happens that if I can take, for instance, if I want to show that n into q raised to t minus 1 by 2 is less than 1, right, or I may even want to show that this tends to 0. So, let us take q is equal to 1 minus p, that is less than or equal to e raised to minus p. So, because I am using this inequality 1 minus x is less than or equal to e raised to minus x, right. This is a useful inequality which is usually used in this kind of calculations. So, here q is equal to 1 minus p, that is less than or equal to e raised to minus p. So, I can substitute here in this thing. So, n into e raised to minus p into t minus 1 by 2, right. T minus 1 by 2, this is what. I want this to tend to 0, right. Now, what is the correct value I can put for this? So, it so happens that if you take p equal to 6k log n by n and t equal to n by 2k, this will come. You have to take p greater than or equal to any value greater than 6k log n by n, and then so if I want to prove that suppose if the kind of independent set I was trying to see was n by 2k, then we can show that this will tend to 0. You have to substitute it here and do the necessary cancellations. You can show that this will be equal to, yeah, so you can substitute by n into, so if you cancel out we will get n raised to minus 3 by 2 into e raised to p by 2. This will become p, because p is at most 1, we can put it as root e by root n, and this will definitely tend to 0 as n tends to infinity, So therefore, so though I have skipped some calculations, so because we have to finish now, so it can be easily checked out by the students that when I substitute p equal to this and t equal to this thing, this will tend to 0. So what we have now told is that if I had selected the value of p to be greater than 6k log n, then I am sure with very high probability that we are not going to have an independent set of cardinality n by 2k. That means my chromatic number is going to be at least 2k. But now what we have to verify is that, is it true that the girth also will be high, that means there will not be any short cycle, but this will not happen with this value. So we will have to make sure that the girth is high, we have to find a different technique. That is what we will describe in the next class. Since we do not have time in this class, we will describe in the next class. Thank you.